Okay, in this video, I want to discuss the effect of intermolecular forces, the forces of attractions that are present in between two molecules, could be two atoms, could be two molecules, that might be present in any substance. So, usually, if you think about these sometimes are also referred to as the Van der Waals forces of interaction. And we'll discuss this in a greater detail, actually, what kind of interactions are possible in chapter 11 when we discuss liquids and solids in a little bit more detail. But realize that these are only weak forces. These are weak forces. And usually they do affect the physical properties of any material. So if these are typically small in gases, because gases usually have molecules far apart from each other, so one can say that gas molecules are oblivious to the presence of each other. They don't really feel the attraction. Do not feel. No feel. Let's just call it no feel. Of attraction to another molecule because they are so far apart. The distance of separation in between them is quite a lot. Now, if you think about a system which is being maintained at a higher temperature, perhaps one can still say that the forces of interactions are not going to matter, because if the temperature is high, that would mean that the kinetic energy is going to be high, and so the molecules might actually go through a collision. They might collide many times, but a weak interaction, a weak attraction is not going to be a significant amount of force that can cause any big change in the force per se, and hence the pressure. On the other hand, if the temperature is low, and the collisions are slow, in that case one can say that these weak attractions can actually affect the collisions. You can perhaps think about it through the same example that I gave you in one of the videos when we discussed the billiard balls. And let's say now you kind of put some kind of like a sticky material on the surface. Now, if the billiard balls are moving way too quickly, what's going to happen? If the velocity is really high, they're going to come in. They might even see the stickiness on each side. They will collide and then perhaps still continue to move. So the effect is not going to be dramatic. However, if the two spheres are moving with a lower speed, aka in gas molecules you should think about a lower temperature, then it will have a greater probability that these two actually might stick to each other. In other words, the effect of these weak forces between the two atoms that might become more predominant in case of lower temperatures. Now, as you can see, let's erase parts of this. As you can see on this graph, that as we have increased the temperature, the ideal gas behavior, which is shown in a red curve, and xenon, both of those match up, so they coincide. Whereas when the temperatures are low, so to the tune of 200 Kelvin, they show deviation, significant deviation in the system, and one can actually see that the pressure in atmospheres is a value lower as compared to the pressure that is exerted by the ideal gas. So one can expect that if the temperature is lowered, then the ideal gas behavior will see a deviation. It would not be followed, and that the pressure is going to be lesser. It's going to give you lesser value, and the reason for that is because you have the weak attractions between particles, and hence that's going to lead to decrease in the number of collisions with the surface of the container, and hence it will essentially lower the pressure of the system, as you can see here. And this is across the board. So if you think about molecules, polarity, and we are going to again discuss this a little bit in detail in chapter 10, but polarity is essentially a way to see if in any bond you can generate a delta negative and a delta positive end on that bond. So let's say you have HCl. Chlorine is more on the right side of the periodic table. It has a tendency to pull the electrons towards itself, and hence it's going to have a slightly negative charge that will force the hydrogen to go with a positive charge. Compare this to a bond between hydrogen and hydrogen. Hydrogen would want to pull electrons towards itself, but so will the other hydrogen. So in other words, one can say that the effect of one is nullified by the effect on the other, and hence the net electron density kind of stays in between. So this kind of a bond is also called as a non-polar bond. On the other hand, if you consider HCl, in that case, Cl is going to pull electrons towards itself and take up the negative charge, whereas hydrogen is going to go with the positive charge. Since you have actually generated two charges in the system, you would say that this is a polar bond. And in general, whenever we have polar bonds or molecules containing polarity, in that case, you can say that the number of interactions is going to be higher. Number of interactions is going to be higher. Don't you think if the number of interactions is going to be higher, that would mean that the deviation from ideal gas behavior is also going to be higher, which means that if you have something like water, HOH, okay, this is a polar molecule because there is a difference between the electronegativity between oxygen and hydrogen. Oxygen is the slightly negative terminus, whereas hydrogen is the positive end of the molecule. And now if you compare this to something like chlorine, Cl2. In the case of water, okay, let's forget about chlorine for a second because that has additional factors, but let's consider something of the same size, maybe something like CH4. CH4, you have carbon hydrogen bonds. Now there is not as much electronegativity difference between the hydrogen and carbon, and as you know, electronegativity is the tendency to pull electrons towards itself. You can envision that as a tug of war for electrons between hydrogen and carbon, and the rule is that if there is an element which is more on the right side of the periodic table, it will have a tendency to pull electrons towards itself to a greater extent. So methane, as you can see, both of these are non-metals, and carbon is kind of more towards the middle on the periodic table. So methane is pretty non-polar in that sense. And if it is non-polar, then that means that the correction that you should see for methane should be less. And indeed, the value for the correction is a low value. It's only about 2.25 for the case of methane, CH4, and for the case of water, that value is actually a big number, 5.46. Again, you don't have to memorize these numbers, but just realize that greater is the polarity for a particular molecule. That would mean that you have a greater deviation from ideality, and hence the larger number of interactions are going to give you a greater deviation from ideality, and hence the pressure value is going to go down significantly. So let's take a look at what combining the volume and combining the pressure component, essentially what should your ideal gas law, what should that look like? We'll call that a real gas law, and we'll call it a real gas law because we're in this case looking at specifically the deviations on the pressure, the deviations on the volume. So the previous video that gave us a volume correction of V minus NB, and van der Waals' work essentially gave us the pressure to be pressure plus a n square over V square. So pressure times volume is equal to nRT, and that is the new equation which will be called as the van der Waals equation, and sometimes also called as the real gas equation, where P is the pressure, A and B are the pressure correction or force of interaction correction, B is the volume correction, N is the number of moles, capital V is the volume of the gas, the total volume, R is the gas constant, it has a specific value of 0.08206, and T is the temperature in Kelvin. So if we are talking about a real gas, this is the equation that we are going to choose to use.